who's been the coordinator for the whole project with a little bit of help from me. The 7 people who are the steering committee are represented here today by yours truly. All the rest of them are traveling, although many of them are going to be logging in remotely, especially tomorrow, when we're going to continue the AGORA part of the meeting Saturday and Sunday. Ji-Hun has been playing an absolutely crucial role in the entire project. First as a postdoc here with Mark Krumholtz, then as a postdoc at Caltech, and now as an Einstein Fellow. One of the places that you can look for all the AGORA results, working papers, and so forth is agorasimulations.org. Just Google AGORA simulations. And then there'll be various other ones that I'll mention. So we currently have 110 participants from 57 institutions in at least 8 countries. And we're going to be calculating the results on cosmological simulations based on 8 different initial conditions representing 4 different mass scales, 10 to the 10, 11, 12, and 13 solar masses at redshift 0, and with 2 different merger histories, one with many mergers, another with few mergers. All the astrophysics will include mass-dependent gas cooling, the Hart-Maddow UV background, the latest version of that, metal and energy yields for type 1 and 2 supernovae, etc., and better than 100 parsec resolution and a high star formation threshold, which, as we learned in 2011 in the ERA simulation, which was led by Javier Agudes here, working with Pierre Maddow, and in other recent simulations, this seems to be the key to getting realistic galaxies, including the internal properties. Of course, many of you know that in 2012, Cecilia Scannapieco published the Aquila galaxy simulation paper, which compared 13 different simulations of the same initial conditions, but using, in many cases, quite different physics. And the paper says that all 13 were a dismal failure. Not one looked anything like a real galaxy. They all had big peaks in the angular momentum divided by the angular momentum required for circularity. They had big peaks around angular momentum 0, but a big spread out to large angular momentum. There's just no galaxies in the world that look like that. So it was a horrible failure. Those simulations had resolutions typically of half a kiloparsec or so. And such simulations simply cannot resolve the internal structure of galaxies properly. Another feature is that all of the simulations in the AGORA project are being analyzed by the YT combination of analysis code and visualization. They can all be read by YT, and a little bit more on YT in a minute. And that's going to be crucial for comparing them. We're going to store, for the cosmological runs, 200 time steps, and we've agreed on which redshifts to store. So we'll have a lot of data. Of course, people are encouraged to store more time steps. So here's our official poster, courtesy of Ji-Hun Kim and Fabio Governato. So enabling technology, Oliver Hans, multi-mass initial conditions, and we have a common cooling code called Grackle with APIs that will make it easy to use with C code or Fortran code. We are comparing everything, as it says, with YT, and we have many variants of the common analysis codes. All of the ones that are currently used are represented here with only one exception, and that's a repo, and we're hoping that the repo gang joins. So the goal is a collaborative multi-platform study to raise the realism and predictive power of galaxy formation simulations. And we have a website, we have a large computer allocation at the National Energy Research Supercomputing website. That's at Lawrence Berkeley Laboratory. And so every team will have a workspace of at least 10 terabytes that's their own. They can control it, and they don't have to let anyone else look at it. But all the tools are available there, and I'll tell you a little bit more about the tools. And this exists now. And people are starting to actually put outputs there. We can convert that 100 terabytes, which is our current allocation, into permanent archival storage. And they tell us that if we need more, no problem. And all 110 members of AGORA can have accounts in that system. We're going to set those up this weekend for the people who are here. So common initial conditions, which exists for all the codes now. Comparative analysis made easy by the YT platform. And many working teams, led by postdoctoral level people in most cases, to do quick analyses. The flagship paper, as we've been calling it, was published in January with Ji-Hun as the first author and about half the members of the team as co-authors. Our rule was that only people were listed here who actually contributed to this paper. So the goals are, broadly speaking, to raise realism and predictive power of galaxy simulations and the understanding of feedback processes that regulate galaxy metabolism. So one of the examples included in that flagship paper was this common analysis using YT of the output from 9 of the codes. And the ART code, the version that's used at New Mexico State, led by Anatoly Klipin, has now also run this initial condition and is also doing the high-resolution version. And if you look carefully at these, you'll notice that there are slight differences. And if you look at the subhalo structure and the statistics, the differences are actually quite significant. And you really see the good features and the bad features of adaptive mesh codes like ART, ENSO, and Ramses compared to the Lagrangian SPH codes like Gadget and Gasoline and various variants. But the key thing to appreciate is that all of these were analyzed in parallel by YT. So the music initial conditions can be specified by just giving a single parameter file, and then the initial conditions are generated in the appropriate format for all of the different codes. And the new feature is that Oliver Hahn, Jose Anorbe, and Ji-Hun Kim have now carefully produced initial conditions that are ellipsoidal in the innermost high-resolution region. And they've checked that this region will not be disturbed by the larger mass particles on the outer regions by running the simulation at pure dark matter simulation all the way to redshift 0. This is going to be the basis for 2 of the 3 papers that we're going to try to push forward this summer. The high-resolution version of the 10 to the 11 solar mass with dark matter only and resolution better than 100 parsecs, the Grackle cooling code implemented in the hydrodynamic version, also with this same initial condition, and testing common star formation and feedback recipes using an isolated disk initial condition, which was generated by Oscar Agertz, I think, and Romain Tessier, and a number of the different groups have already run that. And that's available. And of course, all of the initial conditions and everything that we're doing in the project, except the outputs from each individual team, are available to the world. And we welcome additional participants. So this is examples of 4 different codes running the initial condition for this isolated galaxy. The idea is that this is supposed to represent a Milky Way type galaxy at redshift 1 or so with maybe 20% gas mass in the disk. And the point is that the cosmological simulations will take a while to get down to these low redshifts. So this is a chance for each code to tune up their star formation and feedback prescription on something that will resemble a fairly nearby galaxy. And as we say here, this is only preliminary. The physics has not yet been carefully calibrated across code. So this is just to show you that all of this stuff is happening. YT has now been released just last week in version 3.0, and the new features in 3.0. So YT is a very elaborate combination. It's basically a toolkit for analysis and visualization of any volumetric data. And it's beginning to be used widely, not just by astrophysicists, but by geophysicists and others. Now we support particle data. SPH data can be smoothed onto adaptively defined mesh. It supports octree AMR codes. That's the main new feature with 3.0. So that means that Ramses and ART, which are octree codes, in other words, they have meshes that are not necessarily rectangular, are supported. And there are new front ends for ART, ART.io, Boxla, et cetera, Tipsy, FITS files, et cetera, as well as rewritten front ends for Enzo, Flash, Athena, and generic data. So in addition to the codes I've mentioned, this supports many other codes. And I think very quickly, YT is becoming a default analysis tool. So these are examples of other groups that are using YT, not part of AGORA. Actually, in some cases, part of AGORA, but these aren't the specifically AGORA simulations. So these are just a few examples. And I urge anyone who wants to learn more about YT quickly to just go to the YT-project.org website, where you'll see many, many more examples, and you can download YT and quickly get it working on your laptop. Grackle is now available in two modes, non-equilibrium and equilibrium. We're assuming that equilibrium is the default for high redshift galaxy formation, although non-equilibrium cooling is much more realistic. It's not going to make a lot of difference at low redshift. And it's now fully documented. These are examples of the cooling functions taken from these images are taken from the flagship paper. And so between the flagship paper and the Grackle documentation, you can learn all about it. And I think Grackle is now working for all 10 codes except possibly gasoline. And the hope was that it would be working with gasoline by the end of the week. We'll get a report on that tomorrow. So this is the YT analysis toolkit, and this is just a list of the various codes that are supported and what aspects are supported. I realize this is hard to read, but of course this will all be put up on the web. And a lot of people, including many people who are here, have been working hard to make sure that all of this stuff is really working. The University of California High Performance Astrocomputing Center, which is helping to support this meeting, has been supporting 4 working meetings of the YT group working with the AGORA people especially. So we're trying to make this very widely available. We have now built the entire data analysis pipeline using YT on the National Energy Research Scientific Computing Center at Lawrence Berkeley Laboratory, which, as I said, everybody associated with AGORA can have an account on. And we, thanks to Alex Bogert and Miguel Rocha and other people here at UCSC like Vince Steffens, and especially Matt Turk, who created YT, we have many, many capabilities. So for example, we're going to demonstrate this tomorrow for people who are still here. We can take the output from YT, any output from YT, put it on the latest, greatest NVIDIA cards with 3,000 cores and 12 gigs of RAM, and instantly generate high-resolution displays, which we can ship out at whatever your internet speed is, up to 30 frames a second. And if you have the capabilities, we'll do it in 3D, in other words, stereo. And we're going to demonstrate all that here. It's quite amazing. There are sliders and buttons that you can assign. You can change where you are in a simulation. You can change the thresholds. You can change the color codes. You can explore your data as if you're really interacting with it live. It's an amazing experience. How many people here have actually done that? Okay, so several people here have actually seen this. This is not vaporware. This exists. And these remotely rendered images can be streamed to your IPython notebook, or for that matter, just using HTML5 to your browser. And you don't need to install anything. You just happen to have an account at NERSC and you have to SSH in. So we're using the Edison machine, the latest supercomputer. It's, I don't know, 200,000 cores or something like that at NERSC. And we've been given 5 million CPU hours for analysis and 100 terabytes of storage, which we can make permanent. And we can get more as we need it. So the papers that we're going to be especially trying to finish, working on them this weekend and trying to finish them very soon, are the proof of concept paper where we're doing the analysis in parallel of the pure dark matter high resolution simulations. That's paper 2. Paper 3 is including Grackle and doing a simple galaxy simulation just to make sure that all the codes are properly implementing the cooling. And then paper 4, calibrating the star formation feedback recipes on an isolated disk galaxy. And so this is the codes that are currently doing all of those and who are responsible. We have 4 working groups developing the software to make all of this possible. And we have 9 science working groups. And on the left-hand side are the names of these working groups. So cosmological initial conditions, et cetera. And for the science working groups, isolated galaxies and subgrid physics, dwarf galaxies, dark matter, satellite galaxies, galaxy characteristics, outflows, high redshift galaxies, interstellar medium, and the black hole and feedback prescriptions. And these are the leaders of each of these groups. Many of them, of course, are here. So this provides a unique opportunity to validate our answers to long-standing problems in galaxy formation. And I think it's about time that we do this. And the goal is to raise the whole world community's level of ability to simulate and to understand the results of the simulations. I think that over the last few years, galaxy simulations have become much more realistic. We're still not simulating, I think, all the relevant physics. And of course, the key physics of star formation feedback, including black hole feedback, is on scales of AU or so, whereas the best scales that we can simulate, even in isolated galaxy simulations, are parsec or so. And in cosmological simulations, 10 or so parsecs. So that means that a tremendous amount of the physics is subgrid. And the subgrid physics necessarily will be different in the different implementations, partly because of the difference in of the implementation and partly because of different physics choices that we're making. And that's why there is no question that the results of the different codes are going to be different. And that's why we're going to need to look carefully at them and understand them. And that's what we're going to need to do to move forward. Of course, at the same time, there's continuing work by other people doing extremely high resolution simulations of an AU or better, where they're actually trying to simulate the real physics of star formation and feedback and AGN. And that's critical to combine with these galaxy scale and cosmological scale simulations in order to continue to improve the whole scheme. That's all I prepared. Any questions? Sandy.
So this is, a fantastic undertaking, and as you've said, it's about time. What are your criteria for success?
I think that on the one hand, just being able to run and compare the simulations is already novel, and it will be a success.
Yes, that's a
But more important, we want to be comparing to fundamental physics, and it's critical that people like Mark Krumholtz, Charlie Conroy here, and also other experts who are really interested in the fundamental physics of star formation and the feedback, et cetera, are carefully looking at what we're doing and participating in AGORA. And we also need to compare with observations. Now, of course, we're only running 8 initial conditions, so we're not going to get anything like a statistical sample. On the other hand, the same codes, having been validated or at least understood, can be used and are being used to run many more examples. For example, Phil Hopkins' Gizmo code being used in these fire simulations, that code has already been run on a dozen or so different initial conditions. And he's running it on the AGORA initial conditions as well. Yes, Sandy?
I still didn't hear a clean statement about success.
Well, I think we're going to have to judge as we go along. But to the extent that we're seeing the features that we see in real galaxies when we compare to observations, that'll be good. Of course, if we don't see things that we should see, that'll be bad. And let me just mention, I forgot to mention this, that included in the pipeline that we've built, this is Miguel Rocha's work especially, at NERSC, is Sunrise. So all of Sunrise is fully implemented, and that means that anyone who's run their code through the YT scheme can get realistic images in any waveband, and we're going to make it possible to generate full high-resolution data cubes for IFUs. And of course, you can then use those to put slits. And so that's going to be another option to compare with observations.
I've now asked you 3 times, and each time you've reverted to telling me what you're doing.
Well, what would you suggest that we use as a criterion for success?
I suggest that you really think about it.
Okay. We'll do that over this weekend.
Okay.
What's the criterion for good observational project?
That's true too.
Eric?
So I,
you always could repeat your very worst results with very worst results. No problem.
well, no, so I guess what I heard is that the communication between the different groups, the development of common infrastructure, and the ability to have meaningful conversations based on exactly the same sets of physical processes and initial conditions. I mean,
And exactly the same analysis.
Have a conversation.
Yes, yes.
I guess the part that I would add to that is that you're going to learn not when your models are successful, but when they're really unsuccessful.
Sure.
Because then you realize that there's a problem with the model.
In many cases, we aren't even going to know how successful they are. We'll just know that they're different.
Well, so I guess, but that's where I guess a meaningful and well-considered comparison with observations could be quite useful. And I think that it's really important there to also think about, to be kind of very honest with oneself.
Sure.
Because we're all very excited about, oh, this simulation looks less bad than what we had before, so we'll say these are wonderful. But
right.
They're really not. They're still overcooling or whatever. And so I think to be very, very honest and frank as a way of trying to make progress and elevate the level of the conversation.
I think we all agree. And so let me just explain one more thing. So each team, each different code group, and there's currently 10, will have their own workspace. And they don't have to share any outputs they don't want to because they'll have their own permission. They can then change the group the permission to group permission, and then they can let other people look at it. So when they're happy, fine. But the idea is not to do a getcha, but to let people, be sure that they understand what they're doing well enough to make it available to the other members of the team. And then ultimately, we expect that all of these results will become public. And as I said, our working papers are public all the time. You can find complete documentation at the websites. Any other questions? Yes?
Some of the runs are going to be, in the massive scale of zooms, going to be extremely expensive.
Yes.
I'm wondering if you had explicit estimates for the CPU hours required for each code.
My guess is that altogether, we're talking about something like 100 million CPU hours. The expensive ones are certainly several million CPU hour runs for many of these codes. And one of the things that we tried to do, I tried to coordinate a big proposal to get a lot of computer time that the group could use, in the US at least, but it was not successful. So far, what I've done is to get analysis time at NERSC, and I'm afraid each group is responsible for getting their own supercomputer time. My own personal supercomputer time that I share with Anatoly Klipin, Daniel Severino et al. This year is, 25 million CPU hours or something like that. So it's possible these days to get a lot of computer time. I hope that that isn't going to be a stumbling block. Many of the Europeans also have lots of computer time. So I think it's quite realistic that we can do all these simulations. Of course, even with all the time, the simulations will take clock time. The results aren't going to come immediately. And so, of course, we have to start soon. Okay, if there aren't any other questions, I think we should move on to the next talk.